Okay, our next step in looking at acids and bases is looking at acids that can donate more than one hydrogen. And so these are called polyprotic acids. Poly meaning many, and protic referring to the hydrogen ion that they can donate. And here's what happens. With these polyprotic acids, they simply can contribute more than one hydrogen ion. Okay? So each time they contribute a hydrogen ion, this essentially increases the H3O plus concentration in the solution. And technically then, if you increase the concentration of H3O plus, then you should be changing the pH. And that would actually cause a decrease in the pH. So this is what this looks like. Okay? So phosphoric acid here is an example of a polyprotic acid. And what it can do, since it's H3PO4, it can eliminate, or it can produce 3 hydrogens and put them into the solution. But what that would look like then is this. If you have H3PO4, that's going to react with water. And this is a weak acid, so it will have an equilibrium. But only one of those hydrogens leaves, at least in the first case. So you will get H3PO4, but then there are still 2 hydrogens left, and that H2PO4 has a 1 minus charge. This right here, with this charge, seems to be an issue that people are having. Okay? So you really need to realize that if you lose a 1 plus charge, then this becomes a minus charge left over. Now, this process has a Ka to it. And you can find that Ka in the back of the book. Okay? But I'm just going to write this Ka down. It's 7.5 times 10 to the minus third. Okay? Now, this compound still has a hydrogen that it can give up. So there's another expression that we can write with H2PO4, which is a minus charge. That can now react with water, and it's still an equilibrium. So I'm going to get yet another hydronium ion. That means between these two, our hydronium ions have increased, haven't they? Okay? Now, that leaves us with HPO4 with what charge? And it should be minus 2. Okay? Now, this also has a Ka value. And that Ka happens to be 6.2 times 10 to the minus 8. Okay? So, one of the things that you should have gotten from one of the worksheets that we did is, as this gets smaller, okay, we get shifted further and further to the left. Okay? Now, the other issue is there are 2 Ka values here. So how do we distinguish them? Well, this one, the first one is called Ka1, and the second one is called Ka2. So you have your first ionization constant and your second ionization constant. But we still have this compound which still has yet another hydrogen that it can give up. So there is a third equation, which would be HPO4 minus 2 plus H2O. Still an equilibrium. So I'm going to get yet another H3O plus PO4 3 minus. And since this is yet another Ka, this is Ka3. And that Ka happens to be 4.8 times 10 to the minus 13th. Now, all of these Ka values, okay, are actually found in the back of your textbook in a chart. For your worksheet that you'll have today, because most of you don't have your book with you, I put them on the worksheet. So you will not have to look them up, but there's a chart in the back of your book that has all of these. But essentially, what has happened each time here is we have an H3O plus concentration initial, and then we've added more H3O plus, and then we've added more H3O plus. So essentially, each time we do one of these ionizations, the concentration of H3O plus increases, okay? So this is an example of what is called a polyprotic acid. Now, there are many examples of polyprotic acids, okay? And all these can be found in the back of your book, but H3ASO4 is an example of one. And you should be able to tell me that that is arsenic acid, okay? And it will give up 3 hydrogens. H3C6H5O7. Citric acid is another example. It will give up 3 hydrogens. H2CO3, carbonic acid, will give up 2 hydrogens. Even H2S gives up 2 hydrogens. And one thing you'll notice about all of these polyprotic acids is they are typically weak acids. Okay? Now, that is not to say we can't have a strong acid that's polyprotic, because we do have one. Sulfuric acid, H2SO4, is a strong acid that's a polyprotic acid. But all of these acids, no matter what, will do the same thing when you start writing the equations. So if I take carbonic acid, which is H2CO3, it is going to react with water, and that's a weak acid. So I'll get H3O plus, you lose just 1 hydrogen. So you still have HCO3, but then you have to get the charge correct. That's a -1 charge, okay? And literally these are conjugate acid-base pairs. So this is the acid, this is its conjugate base. But that conjugate base then turns into an acid in the next step. So now that HCO3 1- can still give up a hydrogen, and that will become H3O plus CO3 2-. And one thing you should be noticing about these is they all tend to end up in a polyatomic ion. Okay? So, this is what the equations will look like. Here's what the problems are going to look like. So, most problems are going to ask you, what is the pH of this type of solution? Okay? But they are also going to ask you for what are the concentrations of all of the ions in the solution. Okay? So you will see in this problem, not only does it want the pH, okay? So we want to find out what the pH of the entire solution is. We also want to find out what are the ending concentrations of all of these ions. Okay? So we're just going to jump into this problem. At any point in time, if you need to pause this to write stuff down, you'll need to do that. Okay? So, the first thing is, we are starting with this H3PO4. Oops, went too far. Okay? And essentially what you are going to be doing is you are going to be making a whole lot of ice charts. Okay? So we're going to start with the H3PO4, and we're going to write the reaction of that with water. So I get my H3O plus the H2PO4 1 minus. Okay? And here's what's going to happen. I am starting with a 3 molar solution. So I start with a 3 molar solution. Water doesn't matter. I don't have any of this yet, and I do not have any of that yet. So then this is going to change by x, x, and x, and hopefully you are now getting pretty good at these. So this is 3 minus x, this is x, and x. Okay, so what I need to know then is, what is the Ka1 of this solution? And again, you would find it in the back of your book, okay? But the Ka1 for this solution is 7.5 times 10 to the minus third. So my Ka expression for this is the concentration of H3O plus times the concentration of H2PO4 minus all over the concentration of H3PO4, okay? So that's the same as always. So now I just fill in everything. So my Ka is 7.5 times 10 to the minus third. That equals x times x. So I'm just going to go x squared right away. All over 3 minus x. Okay? Now, because this is 10 to the minus third, I can cross out that x. And now I just solve for x. And when I solve for x, I'm going to assume that you can do that math correctly. And x comes out to be 0.15. Okay? Now, remember, x are these concentrations. Okay? So, the H3O plus concentration right now is 0.15 molar. And the H2PO4 minus concentration right now is 0.15 molar. And the H3PO4 concentration is going to be 3 minus 0.15 molar. So that's going to be 2.85 molar. So we've already answered one question. Okay? The questions at the top were what are the concentrations of each ion in solution? We already have one of them. Okay? So I'm just going to go to the next page here, and I'm going to list that concentration because we already have it. So my H3PO4 minus concentration is 2.85 molar. Okay, when we're all said and done. That will not change. Now, our next step then is to have this compound ionized. And I'm going to apologize because I'm going to be sliding up and down here a little bit, and that might get annoying. But I need to make a new ice chart. Okay, so I'm going to give myself a clean page here to work with. So now I have the H2PO4 minus that is going to ionize with water, and it is going to form H3O plus HPO4 minus. And we're going to make this into an ice chart. Now, here are some new issues that are going to occur with this ice chart. Okay? This actually has an initial concentration. Okay? And that initial concentration we actually calculated in the previous problem. So this initial concentration is actually 0.15 molar. Water still never matters. Okay? But then also look at the fact that, oops, can't do that. H3O plus also had an initial concentration, and that was also 0.15 molar. So that's something new. Because this is a second ionization, there is now an initial concentration. We are already starting with some of this. Now, we don't have any of the HPO4 yet. Okay? Now that we have that data, now this just becomes a straight ice chart again. I'm sorry for moving that. So this is a straight ice chart where this becomes minus x, plus x, and plus x. So this will be 0.15 minus x. This is going to be 0.15 plus x, and that's x. Now, there is a Ka2 for this reaction. The Ka2 is 6.2 times 10 to the minus 8th. Okay? It is still the concentrations of the products over the reactants, so I'm just going to write this right away, where my Ka, 6.2 times 10 to the minus 8th, equals this times this. So 0.15 plus x times x, all divided by that, 0.15 minus x. Now, this is interesting math, because first of all, the x's will cancel. And so just off to the side here, you technically have 0.15 times x all over 0.15 left right here, correct? Ooh. So essentially, those cancel. So not only do the x's cancel, the 0.15s also cancel. So that leaves you with x equals 6.2 times 10 to the minus 8th. That is your concentration of x. So this is your x value for that concentration. So that means, okay, my concentration of HPO4 minus is 6.2 times 10 to the minus 8th molar. But now my H3O plus concentration was 0.15, and then we have to add that x to it, which is 6.2 times 10 to the minus 8th. Now, do that math in your calculator. And once you do that math in your calculator, you realize that, you know what, that's a really, really small number that I'm adding to a really big number. So your H3O plus concentration essentially does not change. H3O plus is still 0.15 molar. Okay? So, going back here, or going over a page, I'm going to go over a page. Now, I would have a concentration of H2PO4 minus. Okay, and what you realize, or maybe you didn't realize, sorry, that concentration is right here. And again, you're adding a really small number, or you're subtracting a really small number. So that concentration does not change again. So this concentration is 0.15 molar. But I now also have the concentration, of HPO4 minus, which is 6.2 times 10 to the minus 8th molar. All right? So I have those ions. Now, there's more fun. Because I still have this ion left. So that means I have yet a third ice chart. So now I just have to create yet a third ice chart with this ion. So HPO4 minus plus H2O, H3O plus PO4 3 minus. Now I'm going to get that concentration of that last ion. So we're still making a nice chart. But here's the issue. Okay? What is the initial concentration of HPO4? Well, we have to go back up here, and it's right here. That initial concentration is 6.2 times 10 to the minus 8. Okay? So down here, this is 6.2 times 10 to the minus 8. Water doesn't matter. And so what is the initial concentration of H3O plus? That has not changed either. It's still 0.15 molar. This is 0. So then this is going to be minus x, and x, and we're adding these two. So this is 6.2 times 10 to the minus 8 minus x. This is 0.15 plus x and x. So now we will just set up our Ka3. Okay? So it's still products over reactants, and Ka3 for this particular compound is 4.8 times 10 to the minus 13th. Okay? So we're going to set up 4.8 times 10 to the minus 13th equals 0.15 plus x times x all over 6.2 times 10 to the minus 8 minus x. Now, same problems, get rid of this, get rid of this, but now I cannot cancel anything else out. You need to mathematically solve this for x, and I'm going to assume that you can do that math. And when you do that math, you should get 1.98 times 10 to the minus 19th. Now, that becomes a really small number. But remember that x is also our PO4 3 minus concentration. So that is 1.98 times 10 to the minus 19th molar. But you also have to do a little bit of thinking, because if that x is really small, okay, and I subtract that really small number from that, then that concentration really doesn't change. Okay? So that means now I have the concentration of PO4 3 minus. And that concentration now is 1.98 times 10 to the minus 19th molar. So I've done my job where I've found all of the concentrations, okay? But I haven't been listing the concentration of H3O plus, okay? So if you go back through your data, what you should realize is we technically have to add all of these up. So in the first step, we got 0.15 molar of that. And then in the second step, technically we should add the additional concentration that we got, which was 6.2 times 10 to the minus 8 molar. And then to that, we should add what we got in the third step, which is this 1.98 times 10 to the minus 19th molar. Now, when you start adding all of those numbers up, what you realize is you still get 0.15 molar for your H3O plus concentration. So, all that being said, the H3O plus concentration never changes after the first step. Okay, so essentially you have the pH after the first step. Okay, so you would calculate the pH by using minus the log of 0.15 molar, and that will give you your pH. And you can just calculate that because, well, I'll just do it quick. So your pH should be 0.82. If I did that right. Okay? So this is how you complete a polyprotic problem. Now, the question that's going to come up is, why do I have to do all these steps if the very first step gives me the pH? Because most problems are also going to ask you for what are those concentrations as well.